Welcome to the E-Padchala lecture series in computer science. We are discussing the computer architecture course. In this module, we will discuss the other issues that we did not discuss with respect to multiprocess. So, the previous module introduced us to the cache coherence problem, and we looked at the two different protocols that are used for handling the cache coherence problem. So, this module will discuss about other issues that we will have to handle with respect to multiprocess. So, basically the synchronization primitives, and we will also have an introduction to memory consistency models, though we will not look into details of the memory consistency models. Now, why do we have to synchronize? We basically need to know when it is safe for different processes to use shared data. In a multiprocess scenario, you know one of the main models of communication, methods of communication is using shared memory. So, one processor writes into memory and some other processor reads the data. So, whenever you are looking at shared memory for communication, you have a problem of synchronization. When is it safe for different processors to read or write into the shared data? When you look at the other type of protocol, other type of programming model, namely message passing is explicit coordination with transmission or arrival of data. So, their synchronization is much easier to handle. Whereas, when you are looking at a shared address communication, you need to have additional operators to explicitly coordinate between various processors. These operations can be writing a flag or awakening a thread or interrupting a processor and so on. So, we look at what are the issues for synchronization. So, when you look at synchronization, there are certain primitives that the hardware provides, and using these primitives we normally write user programs, routines, synchronization routines for users to use. So, the hardware has to provide some primitives. One of the basic primitives that any hardware has to provide in order to build synchronization routines is an uninterruptible instruction or an atomic instruction which will fetch and update a memory location's contents. And using this atomic instruction of exchanging the contents of a memory location and a register, you can try to look at building primitive operations, synchronization operations. And when you look at large scale multiprocess, synchronization becomes a major bottleneck. So, if you look at the major problems associated with multiprocess, remember that we pointed out two problems. One was parallelization, available of parallelism in your code. Otherwise, if your code has even some amount of sequential processing, you know the speed up is going to be reduced. The other one is the communication delay. So, when you are looking at communication delay that happens because of communication that will have to happen between multiple processors, synchronization also plays a role, because you need to synchronize certain activities, synchronize data accesses, and this synchronization itself will become an overhead, this will become a bottleneck. So, you will have to look at techniques which will reduce contention and latency of synchronization. Now, when coming to the first and foremost requirement of the hardware to provide an uninterruptible instruction to fetch and update memory, atomic exchange is an example now. When you look at an atomic exchange, we are interested in interchanging a value in a register for a value in memory. So, let us assume that it represents a synchronization variable. We will assume that if the synchronization variable is 0, it indicates that the particular variable is free, and if you have a value of 1, we will assume that the synchronization variable is locked and unavailable. Some other process already obtained access to the synchronization variable and it is unavailable. So, let us assume that a memory location represents a synchronization variable, and if it is 0, it means it is free, and if it is 1, it is locked. So, normally what we do is we set register to 1 and we do a swap between the contents of the register and the memory location. Now, what happens is, if the synchronization variable is free, that is the memory location had a value of 0, and you swap it with the register contents of 1, now the register gets back a value of 0 and the memory location stores a value of 1. So, the new value in register determines success in getting a lock. So, if you have succeeded, you would have got a 0, and it means that you have succeeded in setting the lock. You are the first to get access to the synchronization variable. and if you get a 1, it means some other process already claimed access and you cannot claim access now. And remember that the foremost constraint here is that the key for this whole thing is that exchange operation is indivisible. So the exchange of exchanging the contents of a register and the memory location should be done in an atomic fashion. So you check whether the value is available, you try to lock it if it is available, and at the same time you get an information that you have locked it, and at the same time the memory location gets locked, the synchronization variable gets locked, so that nobody gets access to it. This has to be done in an atomic fashion. So that is the basic requirement. So if you look at this uninterruptible instruction, you know it can be used in different ways. You can look at a test and set primitive. Test and set primitive is basically testing a value to see whether it is available and setting it if the condition is satisfied. So it is the same as before. So you are testing if the synchronization variable contains a 0 value. If so, you set it to 1, indicating that somebody else looking at it will see that it is locked and they will not gain access to it. The other one is a fetch and increment. So you fetch the contents and at the same time increment it. So all of them involve a read operation and a write operation, and basically you will have to remember that it has to be done in an atomic fashion. And also remember the fact that we have assumed that if it is 0, the synchronization variable is free, and if it is 1, the synchronization variable is already locked and it is not available. Now the problem with an atomic exchange or using one instruction which should not be interrupted in any case is that it involves a memory read and a memory write operation, and if we wanted to do it in an atomic fashion, that may have effect on the coherence protocols, because you know you can't give the buses to anybody else during this period, and that may involve a deadlock operation. So instead of bringing in a very stringent requirement saying that a memory read and a write will have to happen atomically, we can also look at making use of 2 instructions instead of 1. So we look at an example here. You can look at what is called a load linked instruction or a load locked instruction and a store conditional instruction. Basically what happens here is the load linked instruction returns the initial value, because load is you are basically doing a read. So the load linked returns an initial value, that is a separate instruction, and then you try to bring in a store conditional instruction, and if when you try to do a write operation on the same memory location, you check what value is returned when you execute the store conditional instruction. If it returns a value of 1, it means that the store conditional succeeds, that is you did not have any other store that happened between the original load and the store. There were no intervening stores. Otherwise, if it returns a 0, it means there was something else which wrote into that memory location, which means your load and store did not happen in an atomic fashion. So that is how you try to look at a load linked instruction and a store conditional instruction. So instead of using one instruction, we are using 2 instructions here. So this is an example showing how you can do an atomic swap with load linked and store conditional. So the first instruction moves the exchange value from R4 to R3, and LL is your load linked instruction. So you are trying to read the contents of 0 R1, that is the synchronization variable's contents, you are reading it into R2. So the read happens separately, and subsequently you do a store conditional instruction where you are trying to load the value from R3 into your memory location's contents. So the write happens here, and check whether the store conditional returns a value of 0 or a 1. If it returns a value of 0, branch 1 equal to 0, then it means your store conditional was a failure. So you will have to go back and do the same operation again. Otherwise, you know it was a success. So your R2 value is moved into R2, which you have read there, is going to be moved into R4, which finishes the operation. Now, so you are separating out these 2 instructions, and you can have other instructions coming in between, but make sure you do not have too many instructions coming in between, then you may not be able to succeed. And any instruction which comes in between and tries to do a store operation on the same memory location will give you a problem. So that is how we are trying to make it a little more easy to implement. by going in for 2 instructions instead of using 1. This is again another example of how to do a fetch and increment synchronization operation with a load linked and store conditional. So, as before, you try to do the first load operation, that is the load linked, and then you bring in an incrementing operation there, and the incremented value is going to be stored into your the same memory location by means of a store conditional instruction. And if something else happened in between, then the store condition is going to fail. So, you are going to go back and try again, otherwise you know that the store condition was a success. So, go ahead and do whatever access you want with the synchronization variables. So, that is how we have tried to solve the problem of having a very stringent single atomic instruction. Now, looking at an example application for these instructions, can we look at building spin locks? Spin locks are a very popular form of a lock, particularly used when you know that the locking latency is very small, and also you know that the locks are going to be released quickly by other processes. So, spin lock basically is like a busy wait. So, the processor keeps on spinning to find out whether the lock is free. If the lock is free, it uses it. If the lock is not free, then it keeps spinning. It does not do anything else, but it keeps spinning for the lock to be free. So, that is why you can't assume that if the lock acquiring the lock is going to take a long time, then the processor is going to waste a lot of time. So, you only look at this spin lock when the latency associated with acquiring a lock is going to be very less, and also locks are not going to be held for too long by different processors. So, this is an example here. So, you have a load instruction first, which loads R2 with 1, and you have your atomic exchange. Of course, this atomic exchange can always be replaced with a load linked and store condition. It is only the concept that is illustrated here. So, you can have an atomic exchange instruction which exchanges the contents of R2 and the synchronization variable which is available in 0R1. So, if after the exchange operation, if you find that your synchronization variable was not acquired, that will be depend on what comes into R2. So, if R2 gets a value of 0, it means that the lock was free and you have got it, and you have also locked the other processors from using the synchronization variable by storing a 1 there. On the other hand, if you get back a value of 1 in R2, then it means that you were not successful in acquiring the lock. So, in that case, branch on not equal to 0, that is if it is a 1, you go ahead and keep trying to do the acquiring of the lock. So, that is a spin lock. So, you are basically keeping on waiting till the lock becomes free. So, this is an example of a spin lock. So, now what about multiprocess with cache coherency? So, the problem with spin locks is that if you are going to execute it with an atomic exchange, which is basically going to read the contents of the synchronization variable and is also going to set it with a different value. And when you are looking at a multiprocessor scenario with multiple processors, what will happen is every time you will have to, and if the lock is available in global memory, every time you will have to go read that, there is going to be a lot of contention for that, and you will also have to check, set it. So, all that is going to lead to a lot of problems, going to lead to a lot of traffic on your bus. So, can we make use of the cache coherency protocol which is already implemented? You know, multiprocessors always implement cache coherency protocol, whether it is a directory based protocol or Snoop based protocol. So, with the cache coherency in place, can we make use of this cache coherency protocol in order to overcome the bottleneck associated with your spin locks? So, basically what we are trying to do here is instead of spinning on the memory location's contents, what you try to do is you try to bring that location to your cache and you try to spin on the cache copy to avoid the full memory latency. So, every processor that normally wants to check the status of the lock, you can that processor can cache that information. There is also another fact that has to be mentioned here, because normally locks also try to exploit locality of reference. So, if the processor tries to acquire one lock once, then it is most likely that it is going to have to gain access to the same lock again and again. So it is better to cache that information in the processor's cache. So that location is cached in your cache copy of the processor, and the processor keeps on spinning on that. When it finds that the lock is available, then it tries to go to main memory, it tries to do an atomic exchange, and it tries to get access of the actual variable by setting the lock there. So this is what is normally used when we look at cache coherency. So instead of doing the read as well as the write on your main memory, which will lead to a lot of memory traffic, we are separating out the read and the write operations. So the read will happen on the cache copy, and once the processor knows that there is a possibility of acquiring the lock because the lock is free, it tries to gain access to the memory location. It may have to race against other processors and it may have to gain access. If it's not successful, anyway it will go back and do the same operations. So the problem, as I mentioned, is the exchange includes a write which invalidates all other copies also. So when one processor does a write, you know it's going to invalidate all other copies, and this generates a lot of bus traffic. So the solution is we start by simply repeatedly reading the variable which is cached. When it changes and you know that the variable is available, then try and exchange your synchronization variable. So this is how you implement locks. When you don't have coherence, you know, this is how we've already explained that without a coherence. But if you have a coherence protocol in place, then you can do the load operation separately. So the load is done. So you read the value, you cache it in your internal cache, a private cache, and you try to keep reading the operation. If the lock is not available, then you keep spinning on it. So if it's a branch or not equal to 0, 0 indicates that the lock is available. So if it's a not equal to 0, then you keep spinning on it. Once you know that the lock becomes available, you are reading a 0 value, then go ahead and exchange your operation. So you are doing a load locked value there. You are incrementing the value of R naught to indicate that it's going to be set, and you are exchanging with the contents of 0 R1. So you are trying to do an exchange operation there. That is the atomic exchange that you are trying to do. And suppose if the value that is returned in R2 indicates that you are not successful in acquiring the lock, then you will have to go back and do the same operation here. And remember that when any processor tries to do a write operation, all the locations, cache locations that were cached by other processors will obviously be invalidated for that particular lock. So you will have to do the process again and again. So this indicates how this process is done for a simple case. So we assume that P0 has the lock and P1 and P2 are trying to get the lock for their own. So when P0 has the lock and P1 begins spin testing, if checking if the lock is available, it is 0. Similarly, P2 also begins spin, it is testing if lock is equal to 0. And as far as the status of the lock is concerned, it is in the shared state because these people have already read it. Now cache miss occurs for P1 and P2, and you may decide to satisfy in any order. So the lock state becomes shared because these people are trying to read it. And what happens is, if the lock is set to 0, when P0 releases the lock, it sets the lock to 0. So P1 gets an invalidate signal because the status of the lock is being changed from 1 to 0 by P0. It's a write operation. So it invalidates the two requests that are sent in. So P1 is invalidated, P2 is also invalidated, and because a write operation has happened, P0 gets the exclusive ownership of the lock. So this is the second step. And then P1 and P2 are continuously trying to gain access to this lock. So there is a cache miss happening. One of them gets the service satisfied. So the cache location goes to the shared state. So the service happens, let us assume, to P2 and write back from P0, and the state becomes shared. And then P1 waits while bus directory is busy. P1 request has still not been satisfied. And P2 checks the lock is equal to 0. It finds that the test succeeds. And now cache miss for the other processor P2 is satisfied. The same thing happens. And P1 and P2 both have read the data. And P1 now tries to execute the swap. It's trying to do a read operation. It's because it sees that it is locked, it tries to do the atomic exchange operation. P2 is also trying to do it. let us assume that P2 gets the lock, gets to do the atomic operation. So, it completes the swap, returns a 0 and sets the lock as equal to 1, and because it has done a write operation, the status changes to exclusive. And similarly, when this does an operation, it invalidates the other cases. It invalidates to the data that has been read by P1 becomes invalidated. Now, P1 tries to do swap completes and it tries to return get the value, but it finds that somebody else has already acquired the lock, so it gets a value of 1. And it knows that it cannot enter the critical section, whereas P2 has already acquired the lock, it will enter the critical section, and the status of the lock continues to be in the exclusive state. And what P1 does is, because it has not got the lock anyway, it will start spinning again. So, the whole process continues. So, this is how you can make use of the cache coherence which has already been implemented. You can make use of that to implement your spin locking without producing an increase in traffic. So, the advantage of this scheme is basically you are trying to reduce the memory traffic. Now, the other types of synchronizations which are possible, we will just mention a few of them. You have barrier synchronization. Now, barriers are synchronization primitives that ensure that some process do not outrun others. So, if a process reaches a barrier, it has to wait until every process reaches the barrier. So, you wait for everybody to reach a barrier. So, that is the synchronization now. Once everybody has reached the barrier, you release all the processes so that they can go beyond the barrier. So, when a process reaches a barrier, it acquires a lock and increments a counter which tracks the number of processes that have reached the barrier. It then spins on a value that gets set by the last arriving process. So, this is an example code that we will see. The barrier synchronization also makes sure that every process leaves the spinning state before one of the processes reaches the next barrier. So, this is an example that we see. So, you have a counter lock as the locking variable. So, you acquire a lock on counter lock, and if count is equal to 0 indicating that you are the first process entering it, you set release is equal to 0 and increment count, and you unlock the count. So, that is a critical section. You will have to gain access to it and then update your count value. And if count is equal to total, which means all processes have entered the lock, you may set count is equal to 0, release the process. Otherwise, the processes keep spinning on release is equal to 1. So, if till release becomes 1, the process cannot leave the barrier, they will have to wait for the other process to come. So, this process, this barrier synchronization implementation has a small problem. Suppose if you have two processes, fast and slow, the faster one leaves the barrier, does some work, goes and does some work and then comes back to the barrier again, and if it sets release is equal to 0, whereas the slower process has still not left the barrier, then you have a problem. The slow process cannot leave the barrier because the release does not support that. Similarly, the other process also, the count anyway, this fellow has not still left, so the count will not tally to total. So, the second process which has entered again also cannot leave the thing. So, you have a deadlock that is occurring. So, that is an example problem that you might have. So, in order to handle this, what we do is either you can look at counting the number of processes that leave the barrier also. Just like how we counted the number of processes that enter the barrier, we can also keep track of the number of processes that leave the barrier. So, that way you make sure that everybody has left the barrier and you do not have a problem. So, you do not allow anybody to enter the barrier again unless everybody has left the barrier from the earlier entry. The other one is looking at a sense reversing protocol. So, sense reversing is you have a local sense, you have the process setting the local sense variable, and every time somebody enters this variable, enters this process, you know you have this is flipped. So, which means that alternatively, in order to release the lock, you see a 0 and a 1. So, using this sense reversing protocol, you will make sure that the problem that we encountered earlier is not repeating. So, when the fast process comes back, it does not change the release, it just waits for it to become 0, and the slow process eventually sees release is 1, stops spinning, does work, comes back and sets release to 1, and both of them go forward. So that is how your sense reversing protocol can help avoid the problem associated with barrier synchronization. So far we have looked at certain synchronization methods. So we looked at an atomic instruction, then we said we looked at a load locked and a store conditional instruction, and we saw how some common synchronization procedures like spin locking or barrier synchronization can be implemented. So the other issue that we will have to discuss with respect to multiprocessors is the memory consistency models. We have indicated what consistency means when we discussed cache coherence itself. So cache coherence basically talks about what value a processor should read. So when one processor modifies the data in the cache and some other processor reads it, or the same processor reads it, what must be available to the processor? That is a cache coherence problem. Cache consistency talks about when, if this data is read by some other processor, will it get the correct information. So to give you a better example of consistency, let us assume that the two sequences that have been shown. We will assume that A and B have been cached by both the processors P1 and P2. Initially there is processor 1 sets A is equal to 0, and at some point processor 1 sets A is equal to 1, and it does a condition checking on B, and based on that it is supposed to execute something. Similarly, processor 2 has also cached A and B is set to 0, and at some point B is set to 1, and the condition checking happens on A is equal to 0. Now if you assume that all this happens according to how we see here, A has been set to 1 by P1 and B has been set to 1 by P2. So when both the processors execute the conditional statements here, you will find that the condition will not be satisfied. So both these conditions are not going to be true. But what will happen if, suppose when P1 modifies A is equal to 1, the write invalidate has not been communicated to the other processor. So the other processor has not seen this value, seen the change in value, and it still assumes that A is equal to 0, then L2's condition will hold good. Similarly, the same argument for L1 also. So what is it that you assume will happen in this case? The programmer writes with something in mind. When it actually gets executed, something else might happen. So you have a problem here. This is an example of a memory consistency. So what if write invalidates and delayed and the processor continues, and what are the rules for such cases? So whenever you have a write problem, you always have a problem. So when you have a read and a write, they definitely have to be ordered in some way. So if the order is violated, what will happen? That gives rise to a memory consistency problem. So recall that coherence guarantees that a write will eventually be seen by other processors and write serialization will happen. Whereas when you are looking at consistency, the consistency model defines the order of writes and reads to different memory locations. So the hardware guarantees a certain consistency model, and the programmer basically attempts to write correct programs with this assumption. So the most stringent of consistency models is a sequential consistency. So in this case, the result of any execution should be the same as if the accesses executed by each processor were kept strictly in order, and the accesses among different processors can be arbitrarily interleaved, and the same interleaving order is seen by everybody. So when you look at sequential consistency, a very simple implementation of this is, sequential consistency is very easy to understand, and an implementation, the processor issues the next access only when its previous access is complete. But the problem is you cannot look at any optimization here. Say for example, when you have sent in a write request, something gets modified. We normally what we do is you will have to send an invalidate, and you will have to wait for all this to happen there, all the invalidates to happen and the write process to finish. Only then you can do the subsequent access. But normally what we assume is we don't have to wait, we don't wait for the invalidates, you write it into a write buffer and assume it will get written. So all these optimizations cannot be done when you go in for sequential consistency. So it is a very slow process. So a better implementation is the processor issues accesses as it sees fit, but detects and fixes potential violations of sequential consistency. So you can basically relax the stringent requirement that is posed by your sequential consistency model. So, you have different relaxed consistency models. So, normally there are two kinds of memory accesses, the data accesses and synchronization accesses. Synchronization accesses determine the order. So, data accesses are normally ordered by synchronization. So, any two accesses to the same variable in two different processes such that at least one of the accesses is a write are always ordered by synchronization operations. And you can try to get good performance even in simple implementation. So, you can look at sequential consistency for synchronization accesses, and data accesses can be freely reordered except of course around sync accesses. So, if you look at the relaxed consistency models, as long as you do not have data races, you do not have a problem. So, what are data races? When data accesses to the same variable in different processes are not ordered by synchronization. So, most of the programs are normally data race free. So, you have relaxed consistency models working fine, and there are many relaxed consistency models as indicated here, and all of them work fine for data race free programs. But when there are data races, if you try to look at more and more relaxed models, you will get a very weirder program behavior. So, you can look at relaxing the constraints in any way. Within a processor, a read can complete before an earlier write to a different memory location completes. Within a processor, write can complete before an earlier write to a different memory location completes. Within a processor, read or write can complete before an earlier read to a different memory location completes, and a processor can read the value written by another processor before all processors have seen the invalidate, and a processor can read its own write before the write is visible to other processors. So, based on what we do here, you have different consistency models. So, relaxing the consistency between read and write, write and read, and write and write. So, depending on what gets relaxed, you have different names like total stored ordering, partial stored ordering, weak ordering, and release consistency. Consistency model is multiprocess specific, and programmers will often implement explicit synchronization in order to be specific. So, to summarize this module, we have looked at the synchronization and consistency issues with respect to multiprocess. Synchronization primitives like atomic exchange and load linked and store conditional have been examined. We have also seen how you can build synchronization operations like spin locks using the primitives. We also have had a brief introduction to memory consistency models. Thank you.